it is section 1.9, the metric of a linear transformation. In the last section, we proved that every metric transformation is linear and the reverse is not always true. That means that some linear transformation is not a metric transformation. However, a linear transformation defined in Rn is a metric transformation. We'll prove this statement by finding the corresponding metric. Here, let's see this example. Suppose T is a linear transformation and defined in R2 and codomain is R3 such that action on E1 and E2, E1 and E2 are the standard bases for R2, and action on E1 and E2 are given in this way. And for this linear transformation, what we have to do is to find a metric A such that these two are satisfied. Let's choose a vector in R2, and then that will have two components, x1 and x2, but it can be written in this way. Now x1, x is x1 times 1, 0, plus x2 times 0, 1, which is same as x1 e1 plus x2 e2. Here, now we'll try to find the action on x. Here, t of x is the same as this one. Now, in the beginning, we assumed t is linear. So by using the linearity of t, we can reach this one. Now, this term can be written in this way. This vector, that vector, collected here, and x1, x2. Now, te1 and te2 are given here so that we can get this metric. T of x is this metric times x. So here, this example is showing that once a linear transformation is defined in R2 here, then we can write the linear transformation as a metric multiplication. That is an example. But for any domain Rn, we can find the corresponding the metric. Okay, here, this is the observation. The metric of a linear transformation is decided by its action on the standard basis. Once action of the linear transformation on standard basis is known, then we can decide the metric, right? That's the observation. So the metric is decided by its action on the standard basis. Okay, here we have a theorem. T is a linear transformation defined in Rn and codomain Rm. Then there exists a unique metric A, m by n. Here, this m is here and n is here, such that T of x is A of x, which means that linear transformation defined in Rn is a metric transformation. As a matter of fact, once Ej is the jth standard unit vector, so that Ej, collection of Ej will be the standard basis, then it can be written in this way. here the action on E1, action on E2. So collection of actions on standard basis. So the metric A is called the standard metric of the transformation. Okay. Okay, here, now we'll see again. And standard unit vectors in Rn is given in this way. E1, only the first component is 1 and every else is 0. E2 is now along with the second component 1. En is the last one, 1. Now, any vector in Rn can be written as here in this linear combination of the standard basis. So T of x is same as this T of this linear combination. Linearity of T makes that. And T1, we collect these vectors T1, T2, up to Ten and x. So if we define this portion as A, then here T of x is same as A of x. So for linear transformation defined in Rn, we can express it as a metric transformation, and the corresponding standard metric is decided by action on the standard basis. Here, that's the conclusion. Okay, let T be a horizontal shear transformation, leaves E1 unchanged and maps E2 into E2 plus 2 E1, right standard metric of T. Okay. Now T, okay, it is saying that T E1 is not changed, unchanged E1, and T E2 is now E2 plus twice of E1. Let's try to write down this one as a vector. That is 1 and 0. And that one is same as, okay, E2 is 0 and 1 plus twice of E1, which is 1 and 0. So that is the same as now here 2 and 1. So the standard metric is collection of these two vectors. TE1 is same as 1, 0. And TE2 is same as 2 and 1. So that is the standard metric. Okay, here we have typo. Okay, that must be B. And we have to put here now okay, I'll change it. Okay. Now write the standard metric for the linear transformation given by that one. We have here 4 components, so that two components in the domain. So it is defined in R2 and codomain is R4, right? Okay. Now here, and we have to collect action on the standard basis. So TE1, E1 is x1 is 1, x2 is 0. So that from here, x1 is 1 is 0. So the 1, second component is 0. Again, this is 1 and 1, right? How about TE2? x1 is 0, x2 is 1. So that here the first component will be now 4, right? There is 4. And again, this is 0. And then minus 3, 0, 1, right? And then finally there is 0. So this is your first vector, second vector, so that from here, the standard metric, we collect the action on E1 and action on E2 as vector here, 1, 0, 1, 1, and second vector is 4, 0, minus 3, and 0. Right? Okay, that is the standard metric for the linear transformation. Okay. Geometric linear transformations of R2. Find the standard matrices for the deflections in R2. Okay. The deflection through the x1 axis, so horizontal axis, defined as here R1, that is the transformation in x1, x2. Now, diffraction through the horizontal axis, then the second component will be changed to be as negative. Okay, geometrically, now consider a point here. That is x1, x2. Deflection with respect to that horizontal axis will make here go down, and this one. This is now x1 and x2. Then it should be x1 and x1 direction same, but x direction is the negation, so that minus x2. Action, this deflection will make that output, right? Okay, so the action is given, so we have to find the corresponding metric. Let's say that is A1, but A1 must be a collection of actions, so that R1 and E1, and now R2, E, okay, no, R2, not R2. Again, same transformation, R1 and acting on E2, right? Okay. E1 is 1, 0. There's here now 1, 0. The image is 1, 0 again. So that first column is 1, 0. And now R2, R1, E2. E2 is 0 and 1. So it's a 0 and minus 1. So that 0, minus 1. That's it for the standard metric of this transformation. How about this one? The deflection through the line x1 is x2. And in the case is we are changing x1, x2 like that. And you can easily figure it out. Okay, for example here. And y and x deflection. Then if we choose a point, then it's deflected to the other side. And you can see easily here now, geometrically, if this is x1, x2, then that is x2, x1, right? You can get quite easily. So for that one, A2 is again same as here now, R2, E1, and R2, E2. The action on the standard basis. Okay, E1, 1, 0, image is 0, 1. So that is 0, 1, just change the position. R2, E2, 0, 1 will be 1, 0. Okay, that's it. Now, third part, the reflections through the line x1 is minus x2. Okay. Now, for this part, the R3 is not given expressly. So you have to find R3 first. Okay. Now, for that one, okay, now we'll see here the figure. Now reflection is made about the line y equal minus x. So if you start with some point here x, then reflection through the line will be that one, right? So that when you check this one, try to use some example. For example, here, okay, the picture looks like, for example, it's x component is 1 and y component is about 5 or 4. Okay, let's say 4. Then after reflection, this will be in now x direction. Okay, same height, but negative direction, so it's minus 4. And now again, that height must be same as that height. Okay, now let's try to make it clearer. So if you are considering here that, for example, triangle, here now, here, that triangle, then that will be basically the triangle, corresponding triangle. So that this height is the same as that one will be the same as that, right? Okay. So we found already x component that's minus 4. If this is 4, that must be minus 4. Now, if this is 1, that must be minus 1. Okay. So we found that this action is done with two steps. First, change the position and put negations. So we can define R3 in this way. R3, x1, x2. That one can be here minus x2 and minus x1. Change the position and change the sign for both. Okay. Now we have to collect action on the standard basis 1, 0, 1, 0, and that will be 0 and minus 1, right? And 0, 1, minus 1, 0. Yay, that's it. Okay, that's the first part. We'll continue in the second part. Thank you.